Okay, so now that we have seen stationary fluids, i.e. Pascal's Principle, pressure versus depth, and Archimedes, let's look at some examples and see how these things actually work. So the first example we're going to look at is for pressure versus depth. So here I have a U-shaped barometer, which is open at the end points here. So this is atmospheric pressure on the outside. And then initially I have water, which is put in here. So initially the water is at a particular level because it's going to be the same height on this side as it is on this side. But then we're going to add some unknown fluid to here. So an incompressible fluid, which is then going to cause this portion of the water to move down so that this thing establishes equilibrium at this location. So here, the amount of unknown fluid that I'm going to put in has a depth of 0.4 meters. And then from the top of the unknown to the top of the water, there's a height difference of 0.1 meters. So using the fact that the density of water is 1,000 kilograms per meter cubed, we then want to determine what is the density then of this unknown fluid that I'm adding to here. Okay. Now, one thing that's true is since this is floating on top of the water, the density of the unknown fluid has to actually be less than the density of the water. And we know that from actually Archimedes' principle, which we'll do some examples of that. And another thing is I had to go around to 4 different stores trying to find some chalk. I ordered some more chalk, but anyways. And this chalk is ridiculously brittle, so it's probably going to break a lot. So if I get frustrated with the chalk, just, you know why. Mostly because I had to waste my time driving around 4 different stores trying to find chalk. So anyways, let's talk about this. So first thing first, so this is the height then of the unknown fluid. Let's call this height here to this exact location the height then of the water. Right? So it's going to be the height of the H2O. Now, what has to be true is pressure versus depth says then that the pressure up here needs to be atmospheric pressure, same thing as here. But since this portion here at the interface between the unknown fluid and the water is exactly at this location here, what that means then is that the pressure of the water here must be exactly the same as the pressure at this interface here. So basically, if I look at this point, let's call that point A, and this point B, what has to be true then is that the pressures at those 2 points have to be the same. So at this interface between the two, those 2 pressures must be the same. So from here, I can then just say that the pressure at A must then be equal to the pressure at B. Well, in this case, we know pressure versus depth says that the pressure at this point up here, which we now know is atmospheric pressure, so I'm going to call that pressure of ATM, plus then, according to pressure versus depth, the density of our fluid, in this case, which is the density of the unknown fluid, times then the height of that unknown fluid, which I'm simply going to call H, times G must then be equal to, on this side, the pressure at this top point here, which is also atmospheric pressure, because again, this is just open to the atmosphere, plus the density then of the water, because that's the density of the fluid in this stage, times then the height of the water, times G. Now, in this case, since this is atmospheric pressure, this is also atmospheric pressure, those 2 things are simply going to cancel. I can subtract both of them from both sides. Since those terms are gone, I have a G here and I have a G here, which means I can divide through by G, so I can get rid of those. So what this tells me then is that the density of the unknown fluid times the height of the unknown fluid must then be equal to the density of the water times then the height of the water. Sorry, I changed notation here. So good. So finally, this says then that what? The density of the unknown fluid must then be equal to the density of the water. Get rid of that. Good. Times then the height of the water divided by the height of the unknown fluid. So in this case, the height of the fluid then is exactly going to be equal to, if I define this 0.1 meters as x, then the height of the water is the same thing as the height of the unknown fluid minus the amount of x. Okay, so it's going to be the same thing then as the density of the water times then the height minus x divided by the height. But that's the same thing then as the density of the water times 1 minus x divided by h. So in this case, you're going to have 1 minus x, which is 0.1, divided by 0.4, so that's a quarter. So multiply through. So this is then 1 minus a quarter, which is 3/4, times 1,000, which is then 750 kilograms per meter cubed. So this is our example of pressure versus depth. So next one we're going to look at is, let's look at now Pascal's Principle, where again Pascal's Principle said that if I apply a force to say like a cork or at least some sort of cross-sectional area in a closed system, what happened in that case then is that what? Again, the change in pressure at the one point is exactly the same as the change in pressure at a different point. So in this case, I'm going to do something like this. So here, let's say this has cross-sectional area A1, this has cross-sectional area A2, defined in terms of the radii. So here I have a radius R2, here I have a radius R1. So what I'm going to do is I'm going to apply a force here. Let's call that F1. And that's going to then generate a force here to then lift my car. I'm going to say, here's my car. Okay? And let's say the weight of my car, so in this case the weight, which is equal to mg, is then equal to 14,700 newtons. Okay? Let's put some more numbers in. Let's say the cross-sectional area of this guy defined by a radius of 1 centimeter, and the radius for this cross-sectional area is defined by a radius of 50 centimeters. Right? So that's half a meter. So what I want to know then in this case is what is the minimum amount of force I need to apply F1 here to raise my car. Okay? So this is what I want to know. So what is the minimum amount of force I need to apply here to generate a force here to then cause my car to move upward? Okay. Now, in this case, minimum amount of force simply means that I want to move my car upward, but I don't want to accelerate it. I just want to lift it at constant speed. Now, since I want to lift it at constant speed, what that means then is that the acceleration of the system must be equal to 0, which means that this must be a static system. So that means then that the amount of force F2 I need to apply here is simply then just equal to the weight. Right? So in this case, we just want some of the forces, say in the y direction, are equal to 0, where I'm counting y as upward. So in this case, I just get F2 minus the weight of the car is then equal to 0, which means F2 then must be simply equal to the weight of the car. Good. Now, Pascal's Principle says that the change in pressure I make here has to be the same as the change in pressure I do here. So here I get the force F1 divided by the cross-sectional area A1 must be equal to F2 divided by the cross-sectional area A2. So from here, we can then say F1 then must be equal to F2 times simply then the ratio of these two areas. And the area here, if I assume that this thing is a circular cross-section with a radius of r, then the cross-sectional area then is simply equal to pi r squared. So the top one's going to be pi r1 squared, the bottom one's going to be pi r2 squared. Those two pi's are going to cancel. So it's going to be the same thing then as F2 times then the ratio of those two radii squared. So in this case, F2 though, we know is simply equal to the weight of the car. So this is going to be the weight times then R1 divided by R2 quantity squared. So it's going to be 1 divided by 50, because again, here I don't have to put it in meters because the units are the same, so they're just going to cancel out, so it doesn't actually matter what the units are. So it's going to be 1 over 50 quantity squared times 14,700. And if we multiply through, what we should find then is the amount of force I have to put is about 5.88 newtons. Okay. 5.88 newtons, that's roughly what? Maybe like 2 pounds, somewhere around there. So not much is that. So I don't have to apply much force to this at all to actually get this guy to raise up. Good. So let's do a few examples then of the last remaining one, which is Archimedes' principle. So the first one we're going to do is not quite a full example, but we're just going to kind of draw some things out and then talk about it and see that this actually makes sense. Right? And then from there, we'll do a couple fully worked out examples. So the first example we're going to say is, so let's say we have an object, which is going to be fully submerged. So here's going to be my object. Okay. So this is my object, where this thing then has a mass. So this is M, and this thing is in some sort of fluid, which then has a density of the fluid, and this thing has a density of the object. Okay. Now, when this thing is under fully submerged, we know this thing has to have a buoyant force. So this is going to feel a buoyant force up this direction. And it also has a weight, so this thing's going to feel by mg down in this direction. And let's assume for now that this thing is going to have an acceleration. Let's say the direction of the acceleration is going to be upward. So let's call this our positive y direction. So let's then look at the acceleration. So let's see what this thing is going to do based off of the relationship between the density then of the fluid versus the density of the object. Okay. Now again, since positive y is upward, let's simply look at the sum of the forces. Sum of the forces in the y direction, which are equal to ma. So this is then going to be equal to what? The buoyant force minus the weight, which is equal to ma. Now again, we know the buoyant force is going to be the mass of the fluid times g minus the mass of the object, but both of these we can write in terms of the densities. So it's going to be the density of the fluid times the volume of the fluid times g minus the density of the object times the volume of the object times g is all equal to ma. Now, in this case, since the object is fully submerged, what that means then is that the volume of the fluid is exactly equal to the volume of the object. Right, so again, as long as this guy is fully submerged, these two volumes have to be exactly the same, which means this volume is the same as this one, which means I can factor it out. So it's going to be the same thing as the density of the fluid minus the density of the object times the volume of the object times g is all equal to, let's write this out too, this is going to be the density of the fluid times the density of the object times the volume of the object times the acceleration. So from here, these two volumes are going to cancel. So we're going to get the density of the fluid minus the density of the object divided by the density of the object times g is equal to the acceleration. So let's talk about three different cases then. So what is this thing going to do based off of how these guys are related to each other? So case number one is what happens when the density of the fluid is greater than the density of the object. Okay. So, well, in this case, if the density of the fluid is greater than the density of the object, this portion here is going to be positive, which means that the acceleration must point in the direction of our positive y direction, which means it has to accelerate upward. Right? So if this was true, this would then correspond to a positive acceleration. So what does this mean? So this means that if I took an object whose density is less than the density of the fluid and I pushed it underneath of the fluid, what's this thing going to do? Well, it's going to feel an acceleration upward. It's going to rocket upward. Right? Now, what's a good example of this? Well, that would be if you had an inner tube, right? We're getting ready to go into summertime. So we had an inner tube because we're going to lay in our pool, if we actually had a pool, but anyways. And then we take that inner tube and we push it under the water and we let it go. What happens? Well, the inner tube goes flying up towards the surface of the water until it pops out and then basically rests on top of the water. Now, again, the reason for that is because the density of fluid, again, in this case is water, so it's going to be roughly about 1,000. Density of air is going to be about 1.29. So in that case, the density of the fluid is much greater than the density of the object, which means that this thing is going to feel a large acceleration. What about case 2? So case 2 is when the density of the fluid is exactly equal to the density of the object. Well, if the density of the fluid was exactly equal to the density of the object, then this would cancel, which means that this would be equal to 0, which means that the acceleration would be equal to 0. So in this case, it would have 0 acceleration. So what would happen there? So that would be if I took the object, which was water, put it into water, and I let it go, what's it going to do? Well, it's going to sit there. So it's not going to accelerate upward. It's not going to accelerate downward. It's going to sit there. Or if I put it in and I gave it a little bit of initial velocity, say downward, it's going to move downward at constant speed. Or if I push it upward, it's going to move upward at constant speed. But the net acceleration, i.e. the net force, will be equal to 0. Okay, so in this case, there would be no acceleration to it at all. Case number 3, the density of the fluid is less than the density of the object. So, what would happen there? Well, if the density of the fluid is less than the density of the object, then this is going to become negative, which means the acceleration is going to become negative, which means that the acceleration is going to be actually in the opposite direction as my positive y direction, which means the acceleration is going to be downward. This thing is going to sink. In this case, a would be less than 0. So, if this thing then is sinking, what would be that? Well, that would be if I took, say, a piece of steel, and I put that into the water and I let it go. Well, steel has, what? I'm trying to remember the density of steel. It's going to be somewhere around like 9,000, 10,000, somewhere around there, which is, what, 9 to 10 times bigger than that of the density of water, which means when I put that in, overall, it's going to feel an acceleration downward, so this thing is actually going to sink. So it's going to accelerate downward. So this is, again, Archimedes' principle. This thing is overall going to feel an acceleration, where that acceleration will be determined by these forces. Sorry, I wanted to get more chalk. All right. So let's do another example of Archimedes' principle. So next one we're going to look at is, so let's put a wood block attached to a spring into a fluid. Not sure if you guys heard that or not, but anyway. So good. So we have this situation. So here is my fluid container. Okay, this thing is filled with a certain amount of fluid. So this is my before picture, and this is going to be my after picture. Okay. So inside of here, let's say I have water. Yeah, large beaker of liquid. Yeah, so this is going to be fluid. Okay, so inside of here we're going to have water. So we now know the density of water, or in this case the density of fluid, is equal to 1,000 kilograms per meter cubed. Now, again, what I'm going to do is I'm going to take a piece of wood. So here's my piece of wood, and I'm going to attach that to the bottom by a spring. Okay. So my spring has a spring constant, which is equal to 500 newtons per meter. And the density of this thing has a density of wood, where the density of wood is equal to 600 kilograms per meter cubed. Now, what this is going to do is it's going to result then in a buoyant force. And since the density of the wood is less than the density of the fluid, we know this thing is going to have to accelerate upward. So ultimately what's going to happen then is that the wood is going to come to an equilibrium position somewhere up here, where the spring has stretched by an amount of delta y. So now my spring is doing something like this, okay? So now what we want to know then is simply, how much did the spring stretch by? So now, initially, let's say that this spring was in its equilibrium position, so this is just sitting on top, so that there was no elongation initially, and that this is the only elongation that's going to happen. So good. So to do this, let's draw a free body diagram. So let's say here is my piece of wood. So we know it has a buoyant force upward, it has a weight downward, it also has a spring force downward. And let's use positive y as upward, and this is going to be in static equilibrium. Right? Meaning that the sum of the forces acting on the object is simply going to be equal to 0. So good. So here the only force upward is the buoyant force. The buoyant force minus the spring force minus the weight is all simply equal to 0. Now, for this problem, the only place that the elongation is going to come from is from the spring force. Because remember, the spring force is k times delta x, or in this case, delta y. So here we want to solve this for the spring force. So this tells me that the spring force then must be equal to the density minus the buoyant force minus the weight. Now again, doing what we did last case, since the object is fully submerged, we know in that case is then the volume of the object is the same as the volume of the fluid. So we can rewrite this then as the density of the object minus then the density, the density of the fluid minus the density of the object, all times the volume of the object times g is then equal to the spring force. But again, the spring force we know is the same thing then as the spring constant times that elongation. Good. Now, from here, we can then say that what? The elongation delta y then is going to be equal to the density of the fluid minus the density of the object times the volume of the object times g, all divided by the spring constant. Now, in this problem, I didn't tell you what the volume of the object was, but what I did tell you was that the mass of the wood here was equal to 1 kilogram. So, since we know the mass, we can use the mass is equal to the density of the object times the volume of the object, which means we can rewrite then the volume of the object in terms of the mass of the object divided by the density. So basically all we want to do is what? Replace that volume of the object by this. So finally what we get then is that the elongation is going to be equal to the density of the fluid minus the density of the object times the mass of the object times g, all divided by the density of the object times k. Now, plugging our numbers, we find in this case then is that the elongation is 0.013 meters. So this is then the elongation of the spring. So this is how far the spring had to elongate to reach and establish this static equilibrium. Good. So let's do one more Archimedes principle. I.e. one more buoyant force problem. And let's look at where Archimedes originally came up with this idea. So Archimedes was tasked of determining if a crown that was given to the king was purely made of gold or if it was only gold plated and made of something else. So Archimedes basically sat around and he was trying to figure out how he would actually do this. And then one day when he was in the bath, he sat in the bath, at least as far as the story is concerned, and then he saw the water rise, and then he realized that, by measuring things like changes in volume, then he could determine the density, and then from that density he could actually then determine what type of material this crown was actually made out of. So from this great way of determining this, apparently the story goes that he ran out of the bath, butt naked, through the streets, screaming, "Eureka! Eureka!" which means I've got it. I've got it. So we're basically going to do this. So what we're going to do is we're going to look at the crown. So let's say here is our crown. And we want to determine then how much the density of the crown is. So if the density of the crown is exactly equal to that of gold, then the person who gave the king then the crown is safe. He's not going to have his head cut off. But if it's more or less than the density, meaning it's not gold, then in that case, off with his head. So, the way we're going to do this is actually the way that we would have done it in lab. So in this case, what we're going to do is we're going to take the crown and we're going to suspend it by a string. So that here's my crown. Okay. In this case, we're going to measure the tension in the string. And then this thing has a weight of mg down in this direction, right? So initially, this is going to be the tension. So this is going to be the tension out of the fluid, which in this case, the tension outside we find is 14.7 kilograms times g. So this is the mass times then the acceleration due to gravity. Okay. So basically this thing has a mass of 14.7. Good. So then we're going to take the crown and we're now going to suspend it in a fluid. So then here now is my crown. So there's my crown, but this thing is now sitting inside of a fluid. So here is my fluid that this thing is in. Now, as we talked about when it came to the lab, what happens in that case then is we now have a different tension. We now have T in, where T in then is basically going to measure the apparent weight of the object. Okay? So in that case, we find is that this is going to be 13.4 kilograms times g. Okay? Which basically just means that what? It appears that the mass or the weight of the object has decreased due to the fact that it's now in the fluid, which is why we call it the apparent weight. So it seems like the mass of it has reduced. Now, what we know from the lab, though, is that the reason for this is that what? It still has this tension out, but the difference now is it also has a buoyant force pushing upward, which means that T in is then equal to the difference between T out and the buoyant force. Okay? Which basically means that to solve this problem, we have to use that. So what we have to say then is that T out minus the T in must be equal to simply the buoyant force. Right? Now, from the buoyant force, we know the buoyant force then is equal to what? The density of the fluid times the volume of the object, in this case, since it is fully submerged, times g. Right? Now, notice from our first free body diagram, though, is since this is in static equilibrium, we also know that T out is the same thing as simply the weight, which means if I divide both sides of this by T out, we're now going to get that what? T out minus T in divided by T out is then equal to the density of the fluid times the volume of the object times g divided by T out, but T out is the same thing as mg. So I'm going to write this as mg, but I'm going to write this as the density of the object times the volume of the object times g. Good. Now, reason for doing that is now we can see that what? The volume, both sides depend on the volume of the object, so it's going to cancel out, so I don't care. They both depend on g, so that's going to cancel out as well. So what this tells me then is that what? T out minus T in divided by T out is then simply equal to the ratio of these two densities. So what I want in this case then is the density of the object. So I'm going to multiply that over here, divide all this other stuff over. So finally what we're going to get then is that the density of the object, chalk makes too much noise, is equal to the density of the fluid times T out divided by T out minus T in. Or in this case, since I wrote all the T's in terms of the mass times G's, so basically all those G's are going to cancel, which is then just going to leave me with the masses. So in this case, it's simply going to be what, 14.7 divided by 14.7 minus 13.4. So if I do that, what I find in this case then is that what? And again, the density of the fluid is simply 1,000 because that is water. So we find that this density turns out to be 11.3 times 10 to the third kilograms per meter cubed. Well, this chalk is killing me. So now if I compare that with things like what, gold and lead, so it turns out that the density of lead, Pb, is equal to 11.3 times 10 to the third kilograms per meter cubed, and the density of gold is actually equal to 19.3 times 10 to the third kilograms per meter cubed. In this case, what we see is that the density of the object is actually exactly equal to the density of lead, meaning that our crown is actually lead, which is coated in some gold, meaning that this thing is not pure gold. So what happens to that poor person that gave the king this gift? Well, off with his head. He's dead. Goodbye, person. That's what you get for lying, I guess, though. So anyways, these are some examples, typical type examples that you do. Again, this is what we should have done in lab, but in the original formulation of the lab. But again, since we're not actually on campus, we can't really do it that way. So we did it the other way. But this is what we should have done. But again, these are just some particular examples.